Yes, and for the introducing the next speaker, I'll now hand over to our host, Theo.
No, I will
Oh,
introduce China.
okay. I'll hand over to our host, Steph.
China Lee holds a master's degree in biomedical engineering from the King's College London. She is currently a PhD student at the Department of Biomedical Engineering at King's College London. Her project focuses on fairness in cardiac imaging. She is currently aiming to find the sources of biases so that she can then find a method to address and mitigate them. China, please go ahead.
Thank you. Um, right, I'll try and share my screen. Okay, lovely. Can you see this?
Yes,
Lovely, thank you. So I'm going to be talking about a recent paper that we published about understanding AI bias in CMR segmentation. So my PhD project mainly looks at fairness, which aims to treat protected groups equally. So what are these protected groups? They are people with protected characteristics, which is illegal to discriminate against. And this includes things like age, sex, race, religion, disability. And there are a few different ways to define fairness. Um, so you can, for example, go for something like equality, where you treat people equally, but you might have unequal or unequitable outcomes. Or you can go for something like equity, where you treat people differently, but you have more fair outcomes. And talking about fairness, lack of fairness can lead to biases, which are unjustifiable differences in performance between these protected groups. NIST has quite a good categorization of these biases, so they group them into three different types. The first is systemic biases, which are caused by the practices of institutions, and this can be things like hospitals, data collection centers, and you can have things like representation bias, where the data that you collect isn't representative of the wider population. You can have human biases, which are cognitive and implicit biases, such as anchoring bias, where the first idea that you learn about is the one that you stick to despite collecting new information. And the one that I mainly focus on, statistical biases, where the value of a predictor differs from, excuse me, the expected value. So there are a few examples in the media of kind of biased results. So, for example, AI chatbots, and I think they investigated in particular ChatGPT, was perpetuating debunked and false medical ideas. This was quite a famous one. Google tagged two photos of African Americans as gorillas, and people thought this was due to the lack of diversity in their training data. In America, they used facial recognition in judicial systems, and quite a few people were falsely arrested and did jail time due to bad facial recognition matches. And finally, Apple was being sued for alleged bias in the pulse oximeters in their watches because they didn't work as well on darker skin tones, and this again was thought to be due to lack of representation in the training data. So there aren't just biases in kind of the wider world, they also apply to healthcare. And I like to think of AI in healthcare as a pipeline. So you have upstream tasks where you have the problem definition, data collection, and data pre-processing. And then you train a machine learning model, which is where my research sits. And downstream, you have clinical decision making, diagnosis, and treatment. And bias can be introduced at any point during this pipeline. And the earlier it's introduced, the more likely it is to be exacerbated further down. So just to give you an overview of what I'll be talking about, having given you the context of my work, I'll be talking about measuring bias in CMR segmentation, specifically looking at race and sex bias, and then understanding the source of this bias by looking at race classification and explainability methods. So what is CMR segmentation? It's cardiac magnetic resonance segmentation, which is used for assessing cardiovascular diseases. From the segmentations, you can extract clinical biomarkers, which are used for the diagnosis, treatment, and treatment planning of different cardiac diseases. In this work, we use 352 end-diastolic and end-systolic images of the heart from the UK Biobank, and you can see an example of them here. The UK Biobank has thousands of cardiac MR images, and this is the ethnicity and gender split of them. So it's about 80% white and then smaller percentages of other minority ethnicities, and approximately 50-50 split in terms of gender. So first of all, we wanted to measure bias in CMR segmentation models by using a model called NUnit, and we wanted to see how imbalance in training data affected segmentation performance. So we systematically varied the proportion of subjects with protected attributes in the training data, with the hypothesis that a more balanced training data set would produce a fairer model, and a more unbalanced training set would produce a model that had better performance for whoever was in the majority. So just to look at the results of that, if you look on the x-axis, you've got where we varied the proportion of females in the data, on the y-axis, the segmentation performance. We interestingly found no statistical differences in dice score, which is a measure of segmentation performance, when looking at sex. But in terms of race, we did find significant biases. So the 50-50, where you would actually expect performance to be equal, the black subjects had a higher segmentation performance, that's the group in orange, and the results were only fair or not significantly different when the black subjects were 25% of the data set and the white subjects were 75%. So we thought this was quite an interesting result because it wasn't what we expected, and we wanted to look further at where this bias was coming from. So we shifted slightly to classification models, and we wanted to assess the distributional shift between black and white subjects. So since there was a bias, there must be some difference in performance, and we want to assess this. So we used a ResNet 18 model, and we had 4 different types of data. As the input to ResNet 18 is normally RGB images and CMR images are grayscale, we had 3 channels to use. So we use either 3 channels of just the image, 3 channels of just the segmentation, or a combination of both, which you can see in the figure. And we want to assess the distributional shift in all of these data sets. So we found, if you look at the results at the bottom, that race could be classified with about 96% accuracy. But interestingly, race could also be classified using just the segmentations with 74% accuracy. So our conclusion was that the distributional shift mainly comes from images, but also partly from segmentations. And this is because the model was able to classify the images with such high accuracy. So then we wanted to localize the source of this bias. Once we recognize it, we want to find where it was coming from. So we used GradCam, which is an interpretability method, to visualize the parts of the image that were being used for classification. This would produce heat maps that show which parts of the image were being used. You can see an example below. So this is actually a picture from one of my holidays of some flamingos. And you can see on the left, the original image. In the center, the GradCam heat map, and on the right-hand side, the image and the heat map. So this is the sort of thing that we were hoping to produce for our CMR images. And what we found, here are some examples, is that the models were using regions outside of the heart for classification, but they were also using model artifacts that came from the scanning protocol. So once we realized this, we want to see whether how important the heart was to these classifications. So we created 2 further data sets. So since the model seemed to be looking outside of the heart, we created a data set where all of the images were cropped tightly around the heart. And then to test whether how much the model was using regions outside of the heart, we created another data set where the heart was completely blurred from the image. And you can see examples of both of those here. So we retrained the model using both of these data sets, and we found that accuracy decreased to around chance if the images were cropped around the heart, but accuracy was much higher, in fact, almost comparable to the original data set, when the heart was blurred from the images. And so our conclusion from this is that there wasn't much kind of racial difference in the heart, but there was some outside of the heart. So going back to our original segmentation experiments, since we saw bias there, we thought that maybe cropping images around the heart would remove some of the bias if we went back to segmentation. So we performed segmentation using the cropped images and found, if you look at these lines, that the bias trend was less, but the bias still existed. So cropping wasn't the solution to removing this bias. We then wanted to see if, for example, in a segmentation network, whether you could whether the bias in the images was being encoded into the network. So just a bit of background, NNUNet is based on UNet. It's a U-shaped model with an encoder and a decoder. So we took the first part of the U and took the bottleneck where the images are sort of the most encoded and performed PCA on these latent representations of the images and found that, as you can see on the right, with the black subjects in green and the white subjects in pink, that they were linearly separable. And so there was some sort of bias being encoded into the representations of these images. But we want to test sort of numerically whether how separable these groups were. So we used a logistic regression model to classify race from these representations and found that it could be classified from these encoded representations with about 95% accuracy. And lastly, we want to see whether any confounders could explain differences in segmentation performance. So we used a linear regression model to investigate correlations between dice score, which is segmentation performance, and confounders, and found that none of the confounders could explain performance in white subjects, but for the black subjects, stroke volume, ejection fraction, HDL cholesterol, and MRI year were significant factors in predicting a dice score. So to conclude, from the first set of experiments, we saw that bias could be seen between different races. Sex bias was only seen in some segmentation models. We performed further investigations into other models and found that, for example, in UNet as opposed to NNUNet, we found some bias there. The scale of the bias depends on the segmentation model. And from these experiments, non-heart regions appear to be a significant source of the bias, which we saw from looking at the GradCam images, but not the only one. And my current work is investigating how these biases can be mitigated. If you'd like to read the paper, it's here. And I want to say thank you to my team and all my co-authors who are listed there. And lastly, I just wanted to end on a couple of resources that you might find interesting. So if you want to learn more about fairness, there's a free book online that you can read. It's called the Fair ML book. You can just Google fairness machine learning book and it will come up. And if you're not much of a reader, there's also this great documentary on Netflix that's made by the fantastic Joy Bilamwini, who wrote the Gender Shades paper, along with her co-author. And it's about bias in different aspects, so like housing, the judicial system, medicine, and it's a great documentary. And I'd be happy to take any questions.
Thank you, Tiarna, for your extensive presentation about your PhD project. I would like to ask you something about datasets. You mentioned you use a lot of the UK Biobank, but can you imagine different dataset sources causing biases inside cardiac segmentation?
Definitely. I think from the first experiment we performed, where we looked at dataset imbalance, we systematically chose which subjects were going to be there. So we did 0%, 25, 50, 75, and 100. But I can imagine that if you had a dataset that was very imbalanced and you just trained using that, there would be some biases that would be present. So I don't think it's exclusive to the UK Biobank. I think it's very much based on how balanced or imbalanced your dataset is.
Yes, thank you. And I got a question from Altair. I hope I pronounce your name right. So what causes the biases in cardiac segmentation?
That's a very interesting question. So we're not entirely sure at the moment. It seems like it might be, as I say, regions outside of the heart. If I go back. Oh, it's not on this slide. But we found that in this study that the black subjects had a slightly higher BMI. And so we thought perhaps if it's looking at regions outside of the heart, that it might be differences in, for example, subcutaneous fat, so fat under the skin, or visceral fat around organs that it might be looking at. But there was no definitive pattern when we looked at the GradCam images of what those differences were. But it does seem to be differences in anatomy.
Okay, uh, thank you. Are there any other questions from the audience? You can raise your hand. I can unmute you if you want.
Yes, I unmuted myself already.
Okay, go ahead.
Sure. Thank you, Tiarna, for a great presentation. I was wondering, maybe a little bit in light of the presentation by Amelia before and the work that we did. Since all the pictures or all the images were from one data set, the UK data set, but then I was wondering about the sources of those images in those data sets, right? So maybe, and that's just a question here, maybe some of the population was based in one particular hospital that uses a particular type of a machine. Maybe the bias was potentially hidden in the metadata rather than in what's available and in the clinical conditions of those patients. And just because we use them from the same data set, it doesn't mean that it was obtained in the same manner. And just the fact that well, people live in areas where they live and they go to the hospitals that they go, right? So maybe the race was just an encoder for the hospital that we're coming from. Have you considered any of that, or is that completely untrue?
Yeah, so we did actually consider this because by chance, as you can see, one of the kind of significant factors for on this slide for black subjects and predictive of their DICE score was MRI year. So we found that just by chance, the black subjects we were using were scanned later than the white subjects. So we thought perhaps the imaging protocol might have changed, and that's the difference that we were seeing. But we looked at that and in segmentation performance, and there was no sort of correlation there. And so all of the subjects were scanned at the same scanning center with an imaging protocol that allegedly has not changed. So based on that, we think it's not a factor of like different images and different scanning protocols. But of course, I wasn't there when they were scanned, so there may be some small differences.
Oh, of course, yeah, but it's super interesting and like nice that you had a look. Sorry, I didn't catch that. Thank you.
No worries.
Okay, one other question in the chat from Nina. Um, if we are unsure about the cause of bias, which seems the case, how could you carry on the bias mitigation without knowing the cause? Uh, do you have some insights on where to start with?
So this is a good question. We kind of carried on with bias mitigation because it's apparent that the bias is there. We haven't found the source of it. We know that it's not in, well, we think that it's based on these results, that it's not in the heart. And we think it's sort of other anatomical features. But as of yet, we don't have a good way to sort of mitigate for these. So if, for example, it is subcutaneous fat, it's quite difficult without even if you control for BMI, which we did in another experiment and found that it didn't affect sort of the bias that we saw in segmentation. Even this is quite hard to control for because if, for example, there have been studies that show that black subjects have different fat distributions, it's quite hard to control for this. So we moved on with bias mitigation with kind of that in the back of our minds and found that I mean, I've written a paper. Hopefully, it will be accepted soon, so I can tell you more. But we found that bias mitigation does work. Even, for example, just oversampling subjects. If you have a small number, you can oversample them to make the performance more fair. But I do agree that not completely understanding the source of the bias can be a sort of barrier to implementing sort of thorough bias mitigation.
Okay, thank you very much for your answers and your interesting presentation. I would like to hand over to Theo for the next speaker.
Yes, so